In today's topic, we will be studying about substances called dielectrics. Dielectrics are non-conducting substances which do not have free electrons, but they get polarized when you subject it to an external electric field. Example, air, paper, plastic, etc. Then coming to classification of this dielectrics, we basically classify it into two types, polar dielectric and non-polar dielectric. So in polar dielectric, these are the substances which have a net dipole moment. So if you take the example of HCl, H plus and Cl minus, it has a dipole moment. So each molecule has a dipole moment. We call this as intrinsic dipole moment. So we indicate it by an oval with one end negative and the other side positive, which shows that it is a polar dielectric. Whereas non-polar dielectrics, the center of positive charge coincides with negative. So there is no net intrinsic dipole moment for each molecule. And example is hydrogen H2, methane, carbon dioxide, etc. Now if you take a polar dielectric, in the absence of an external electric field, these dipoles, which are indicated by ovals, are randomly arranged inside the material, and because of this random arrangement, the net dipole moment becomes 0. But when you apply an external electric field to this substance, see the applied electric field is indicated by yellow color arrow E0. Now these electric dipoles align such that the negative part of the dipole will be towards positive plate and the positive side is towards negative plate. Due to this, within the dielectric, a new field is developed which is called induced electric field, and the direction of this induced field is from again positive to negative inside the dielectric, that is in the opposite direction to applied field. And it was observed that the net field in the presence of a dielectric or inside the dielectric would reduce it by dielectric constant times the applied field. That means E net inside the dielectric is equal to E naught, which is applied, divided by K. And now if I write the net field, okay, the net field would be applied minus induced. We have applied E naught and E ind represents the induced field. So from the first two equations, we can get the induced field as E naught into 1 minus 1 by K. Come to a non-polar dielectric. In the presence of an external, in the absence of an external field, we don't have any dipole moment because each molecule has no dipole moment. As a group also the substance has no dipole moment. So P net is 0 in the absence of external field. But when you apply an external field, see we have kept the dipole in an external field. You can observe in the diagram, the negative and positive charges got separated. So towards positive plate we have a negative charge and towards negative plate we have a positive charge. So it has a net dipole moment now, which is not equal to 0. And then you can observe again the induced field has become E naught divided by, the net field has become E naught divided by K because of electric induction or field induced inside the dielectric. So there is no difference in behavior of a polar and a non-polar dielectric in the presence of an external field. Both of them will induce electric field in the direction opposite to external field, and the induced field is E naught into 1 minus 1 by K. Now look at some more terms which we need to know regarding dielectrics. Dielectric polarization. So we have seen that whether it is a polar or a non-polar dielectric, the dipoles are aligning in the direction of electric field, and due to this alignment, they are getting some net dipole moment. So this net dipole moment per unit volume is nothing but called as dielectric polarization. It's represented by the letter capital P, which is equal to P net divided by volume. Okay, here P net represents the dipole moment divided by volume, and we know the SI unit for dipole moment is coulomb meter by volume is meter cube. So you get the SI unit as coulomb per meter square. And you can also observe here that coulomb per meter square is a dimensional formula of surface charge density. So remember this, dipole moment, dielectric polarization and surface charge density have same dimensional formula. Then one more term, that is dielectric susceptibility. So it tells you about the nature of the substance or nature of dielectric, which is defined as the ratio of P divided by epsilon into E naught, where P represents the dielectric polarization. Just now I told you what is dielectric polarization, per applied electric field divided by E naught or epsilon naught. So it's a dimensionless quantity which is related to dielectric constant K. According to the relation, susceptibility is K minus 1. So you can observe that K and susceptibility are interrelated to each other. If K is high, susceptibility is also high. It's a dimensionless quantity. Then dielectric breakdown or dielectric strength of a material. See, we have seen that whenever a dielectric is subjected to an external field, positive and negative charges are getting separated or getting attracted by electric field what we have applied. So if you start increasing your applied electric field, at a particular electric field, the electrons may come out of the material. We know they are bound to the nucleus, but if the electric field strength is continuously increased, the electrons may come out of the substance. So this particular electric field at which you can ionize the substance or ionize the dielectric by removing the bound electrons or valence electrons is nothing but called as dielectric breakdown. Okay, so the table here shows you the dielectric constant of certain substances and their dielectric strength. For air, we know air and vacuum we take it as 1. So dielectric strength is 3 into 10 to the power 6 volt per meter. That means if you apply a field of 3 into 10 power 6 volt per meter, you can ionize air. Okay, so this is a table which represents the dielectric strength of various materials. So this is all about the dielectrics, and you will find the applications of these dielectrics in the next chapter, next topic, that is capacitors.